Our next course name is Open RAN Architecture and its connection with 5G. Let's get started. Open Radio Access Network or Open RAN is becoming very popular RAN solution when we discuss about 5G communication technology. In this course, we will discuss about first, types of RAN architecture. Second, Open RAN Alliance. Third, ORan defined entities. Fourth, Open RAN benefits. Fifth, ORan reference architecture. Sixth, 5G Open RAN network architecture components. Seventh, what is eCPRI and its connection with 5G? Eighth, deployment scenarios. Ninth, ORan service provisioning. Our next topic is types of RAN architecture. Before starting, first have a look on various terms like what is Open RAN, DRAN, CRAN and VRAN. First, DRAN stands for Distributed RAN. DRAN is a classical setup where remote radio unit and baseband unit are co-located at every cell site. Second, CRAN. Also, CRAN stands for Centralized RAN or Cloud RAN. In CRAN, the BBUs from several sites are grouped into a pool and located in one location. Third, VRAN, also called Virtualized RAN or Centralized RAN. VRAN decouples the software from hardware by virtualizing network functions. VRAN and CRAN are very similar. Only difference is that CRAN uses proprietary hardware while VRAN deploys on top of COTS servers. Fourth, the finally Open RAN where the ORan Alliance made a great job creating a specification for open front haul, mid haul and back haul interfaces. Mobile Edge Computing MEC. It is a solution that gives content providers and software developers cloud computing capabilities which are close to the end. Our next topic is ORan Alliance. Now we will discuss about Open RAN Alliance. The ORan Alliance main aim is to reshape the RAN industry towards more intelligent, open, virtualized and interoperable networks. They are working on ORan to enable a more competitive and vibrant RAN supplier ecosystem. This supports faster innovation to improve user experience, improve the efficiency of RAN deployments and network operations. To achieve goals, ORan Alliance is active in three main areas. First, specifications. New standards for open and intelligent RAN. Second, ORan software community. Open software development for the RAN in cooperation with the Linux Foundation. Third, test and integration. Supporting ORan member companies for testing and integrating of their ORan implementations. We can summarize that the key principles of the ORan Alliance include first, leading the industry towards open, interoperable interfaces, RAN virtualization, and big data and AI enabled RAN intelligence. Second, maximizing the use of common off the shelf hardware and merchant silicon and minimizing proprietary hardware. Third, specifying APIs and interfaces, driving standards to adopt them as appropriate and exploring open source where appropriate. Our next topic is ORan defined entities. Let's get into the topic. First, system supporting orchestration of ORan components. Second, non-RT RIC, logical node enabling non-RT control or optimization of RAN elements and resources, AI or ML workflow, and policy-based guidance of applications or features in NRT RIC. Third, application designed to run on NRT RIC. Fourth, likely to consist of one or more microservices. Fifth, identifies data to consume and provide. Sixth, independent of the NRT RIC. 7th, may be provided by third party. 8th, near RTRIC, logical node enabling NRT, controller optimization of RAN elements and resources via fine-grained data collection and action over E2 may include AI or ML workflow. 9th, logical node hosting RRC and CP part of PDCP. 10th, logical node hosting SDAP and UP part of PDCP. 11th, logical node hosting RLC or MAC or high physical layer based on LLS. 12th, logical node hosting low physical layer FFT or IFFT or PRACH extraction and RF based on LLS. Cloud computing platform comprising first, physical infra nodes to host ORan FCNS, for example, NRT RIC ODU. Second, supporting SW components, for example, OS, VM monitor, container runtime. Third, Mano functions. Our next topic is ORan benefits. Let's get into the topic. Open RAN benefits are first, lower expenditure. Open RAN reduce both capex and opex cost. Second, lower deployment time. With virtualized RAN, benefits like automation can reduce the average time for deploying a site, and a virtualized RAN combined with centralized can be deployed faster than a traditional architecture since the only site installation required is for the radio and power. Third, easy upgrade with no inter-vendor dependency. Easy upgrade options from multiple vendors enables future-proof network evolution. MNOs do not have to depend on the roadmap evolution of a single vendor to roll out new features. Fourth, minimum vendor lock-in. Open RAN minimizes the danger of vendor lock-in. Open RAN vendors' equipment will work with the incumbent and future vendor solutions. Fifth, easy to scale. Open RAN disaggregation of a hardware from software can enable carriers to respond more quickly and in a more targeted fashion to increase or decrease or relocate capacity. Sixth, ability to add massive scale. If required, Open RAN network can be added massive scale using web scale approach. Since edge computing is being deployed by service providers around the world, the edge compute architecture can be utilized for Open RAN, container CNFs, and can be used to push changes using automation to the network using the DevOps model. This indicates that the RAN is essentially following the same development curve as the data center did, with the corresponding benefits. Our next topic is ORAN reference architecture. The ORAN reference architecture is designed to enable next generation RAN infrastructures. It is designed with the principles of intelligence and openness. The ORAN architecture is the foundation for building the virtualized RAN on open hardware with embedded AI-powered ratio control that has been envisioned by operators around the globe. The architecture is based on well-defined, standardized interfaces to enable an open, interoperable supply chain ecosystem in full support of and complementary to standards promoted by 3GPP and other industry standards organization. As we can see in this image, it has functional blocks. First, orchestration or NMS layer with non-real-time RAN intelligent controller. Second, RAN intelligent controller near real-time function layer. Third, multi-RAT CU protocol stack function. Fourth, DU and RRU function. Orchestration or NMS layer with non-real-time RAN intelligent controller, non-RT control functionality smaller than 1 second and near real-time near RT control functions are greater than 1 second are decoupled in the RIC. Non-RT functions include service and policy management, RAN analytics and model training for the near RT RAN functionality. Trained models and real-time control functions produced in the RIC non-RT are distributed to the RIC near RT for runtime execution. First, ORan specification defined an A1 interface between orchestration or NMS layer with RIC non-RT and E node B or G node B containing RIC near RT. Second, network management applications in non-RT RIC receives and act on a highly reliable data from the modular control unit and distributed unit in a standardized format over A1 interface. Third, AI enabled policies and ML based models generated messages in RIC non RT and conveyed to RIC near RT. 4. The core algorithm of non-RT RIC is owned and deployed by network operators. Fifth, these algorithms provide the capability to modify the RAN behaviors based by deployments of the different models optimized to individual operator policies and optimization objectives. RAN Intelligent Controller RIC near real-time function layer. The ORan reference architecture provides next generation RRM with embedded intelligence while optional accommodating legacy RRM. This resides within the RIC near RT function layer. The RIC near RT is completely compatible with legacy RRM and its design is started to enhancing the operational challenging functions such as per UE controlled load balancing, RB management, interface detection and mitigation. This layer has following functions. It provides new functions leveraging embedded intelligence such as QoS management, connectivity management and seamless handover control. The RIC near RT delivers a robust, secure and scalable platform that allows for flexible onboarding of third-party control applications. RIC near RT function leverages a database called the Radio Network Information Based, which captures the near real-time state of the underlying network. It feeds various RAN measurements data to the near RT RIC to facilitate radio resource management. It also provides initiate configuration commands to CU or DU. The near RT RIC can be provided by traditional TEMs or third-party players. RIC near RT receives an AI model from RIC non-RT and executes it to change the functional behavior of the network. Interface reference point A1 and E1. A1 is the interface between non-RT RIC and modular CU which contains near RT RIC. E2 is a standard interface between the near RT RIC and CU or DU in the context of an ORan architecture. Multi-RAD CU protocol stack function. The function of the multi-RAD protocol stack supports 4G, 5G and other protocol processing. The basic functions of the protocol stack are implemented according to the control commands issued by the near RT RIC module, example handovers. Multi-RAD CU function shall be deployed on virtualization platform. This virtualization provides a highly efficient execution environment of CU and near RT RIC with the ability to distribute capacity across multiple network elements with security isolation, virtual resource allocation, accelerated resource encapsulation, etc. The current architecture is using existing interface definitions for F1 or E1 or X2 or XN provided by 3GPP. These interfaces can be enhanced to support interoperation among multi-vendors, and the CU provided by TEMS offer a regional CP and UP anchor for DUs. DU and RRU function. The DU and RRU function includes real-time L2 function, baseband processing and radio frequency processing. The interface between the DU and the RRU provides standard function segmentation, including the DU-RRU lower layer split interface, open front-haul interface, and the CU-DU higher layer split interface F1, which ensures interoperability between different temps. Our next topic is 5G Open RAN network architecture components. Let's get started. Open RAN network architecture is needed to address the specific needs of different mobile operators around the world, and it is expected that vendors will interoperate to create customized Open RAN solutions to meet these requirements. The graphic shows the 4G RAN and core network as compared to the 5G RAN and core. The 5G NR with respect to 3GPP release 15 and later, the specifications require the RAN to become disaggregated grouping of functional elements. The G Node B, which is a 5G base station, is comprised of following functional units. First, Open Radio Unit. Open Radio Unit ORU, which comprises the RF chain to transmit or receive the over-the-air signal and provide corresponding transformation of the analog radio signal and the digital signals. It connects through the front hall to Open Distributed Unit. Second, Open Distributed Unit ODU. The Open Distributed Unit, which handles the lower layers of the baseband processing up through the PDCP layer of the protocol stack. In legacy RAN systems, this runs on a proprietary vendor hardware, but today's software are capable to run on COTS hardware, allows this function to be virtualized. Since it is virtualized, this gives flexibility in terms of placing the processes at different locations, which may include the cell site, far edge locations, and or the centralized locations. These functional layer splits are defined in the 3GPP specifications, and their placement is selected based on type of transport network, fiber, microwave, etc. available to the cell sites. Open Centralized Unit. Open Centralized Unit handles all higher layer functions of the protocol stack from PDCP and functions such as the functions of RRC, PDCP, SDAP, X2U, F1U, NGU, S1U, X2AP, X2C, F1AP, F1C, NGAP, NGC, S1AP, S1C, and OAM. OCU software shall be capable to run on x86 or ARM processors. Our next topic is what is eCPRI, how it is connected with 5G and Open RAN. The Common Public Radio Interface CPRI is an industry cooperation aimed at defining publicly available specifications for the key internal interface of remote radio head or radio equipment and base station unit or radio equipment controller via a so-called front hall transport network. RRH are distributed on the towers every few miles in cities and suburban areas. These RRHs has to be connected to baseband unit setting at centralized locations. The connection between the RRUs and the base station is often referred to as front haul. In 4G LTE, we use Common Public Radio Interface CPRI interface as front haul connection, but now enhanced CPRI, that is eCPRI, is becoming an important technology for 5G and Open RAN. The scope of the eCPRI specification is to enable efficient and flexible radio data transmission via a packet-based front-haul transport network like IP or Ethernet. eCPRI defines a protocol layer which provides various, mainly user plane data specific services to the upper layers of the protocol stack. eCPRI protocol planes. Method to access one or more functionalities via the eCPRI protocol. This method typically involves the transmission or reception of eCPRI messages. The following planes are outlined. C and M plane. Control and management data flow for the operation, administration and maintenance of the nodes. User plane. Three data flows covered by the user plane. First, data flow to be transferred from the radio base station to the user equipment UE and vice versa. Second, real-time control data related to A. Third, other eCPRI flows not covered by other protocol planes or flows. Synchronization plane. Data flow for synchronization and timing information between nodes. Our next topic is deployment scenarios. Figure on the screen shows a list of ORan cloud deployment scenarios. The VNFs are shown at the top, and each scenario illustrates how the VNFs are implemented in either a proprietary network element or on the ORan compliant OCloud. The term OCloud refers to an infrastructure element or collection elements that is based on COTS servers, uses hardware accelerator add-ons as needed, and has a software stack that is decoupled from the hardware. As part of the ORAN cloudification work, scenario B is currently the first priority of focus. In this scenario, the ORU function is provided by a proprietary network element located at the cell site. The OCU and ODU run on OCloud is an edge location, while the near RTRIC runs on a different OCloud in a regional location. Our next topic is ORAN service provisioning. Let's get into the topic. This section explains how to provide ORAN services by using the OAM architecture, which includes the Service Management and Orchestration Framework SMO and the OCloud related management entities. Figure on the screen shows the ORAN OAM logical architecture, and together with the OAM interfaces or reference points being standardized, that is O1 and O2. Use of standardized interfaces enables multi-vendor interoperability and choice for the ORAN operator. O1 supports typical FCAPs and other management functions between the ORAN components and the Service Management and Orchestration Framework, while O2 supports virtual resource management functions and other OCloud related management functions. For ORAN, OAM and management, the primary use case is the initial provisioning of the ORAN service over a RAN consisting of both VNFs and PNFs. This use case demonstrates the orchestration of multiple ORAN components by the Service Management and Orchestration Framework to bring up a complex service. Functions such as discovery or registration and configuration of addressing, versioning, and monitoring are done through the O1 interface using standard protocols and data models. Subsequently, resource and performance updates can be sent from the ORAN managed functions backup to the SMO, and they can be reconfigured as needed by the SMO using the O1 interface. Hope you have understood the concept of Open RAN, its architecture, and various technological aspects related to it. Thank you. See you in the next course. Here I conclude this topic. Hope you understand all the concepts clearly. Meet you in the next topic.
If you have any queries, please get in touch with us by typing your comment in the comment section. Thank you for watching. Do like and subscribe to our videos. So what are you waiting for? Join us for the course and do subscribe to our YouTube channel, and don't forget to press the bell icon. Also, if you like our videos, don't forget to hit the like button and share our videos.